Hello, glad to have you in the last breakout session of the day. This is the Exploration and Development track, and we will be hearing shortly from Deborah Sacrey of Auburn Energy. Deborah Sacrey is a geologist, geophysicist with 44 years of oil and gas exploration experience in the Texas, Louisiana Gulf Coast, and mid-continent areas of the U.S. Deborah specializes in 2D and 3D
Glad to have you in the
interpretation
last
for
breakout session of
clients
the
in
day.
the U.S.
This
and
is the
internationally. She received her degree in geology from the University of Oklahoma in 1976 and began her career with Gulf Oil in Oklahoma City. She started Auburn Energy in 1980 and built her first geophysical workstation using the Kingdom software in 1996. Deborah then worked closely with SMT, now part of IHS, for 18 years developing and testing Kingdom. For the past 8 years, she has been part of the team to study and bring the power of multi-attribute neural analysis of seismic data to the geoscience community, guided by Dr. Tom Smith, founder of SMT. Deborah has become an expert in the use of Paradise software and has over 5 discoveries for clients using this technology. She is very active in the geoscience community, including positions as past president of GCAGS, past president of SIPES, and past treasurer of AAPG. She will be presenting today on A Tale of Two Reservoirs, how machine learning can help define sweet spots in conventional and unconventional reservoirs. Please help me welcome Deborah Sacrey.
Good afternoon, everyone. This is Deborah Sacrey, and as you know, I am a consultant in the Houston, Texas area. Today, I would like to go through and show you 2 case studies I've done for finding sweet spots in a conventional and an unconventional reservoir. So the first thing I want to kind of cover is some of the technology behind what went into the case studies. In this particular software I'm using, I'm looking at data, multiple seismic attributes at one time, and I'm looking at it on a sample-by-sample basis. This gives me a lot more statistical information for understanding what's going on in the subsurface. The data is generally normalized to a variance from the standard deviation so that no one attribute contributes more than any other. Thus, true pattern recognition or cluster analysis is totally unbiased. And the importance of using an unsupervised neural analysis as opposed to a supervised is when we're going in and looking at geology, we really don't know what's down there. So we allow the unsupervised information, the computer, to figure it out and show us what's going on instead of us trying to direct it. Now, the sample statistics are really important. If you're working in a wavelet world and you have a 40 millisecond wavelet, you're going to be mapping a peak or a trough or possibly zero crossings. So you can be sampling that 40 millisecond wavelet 4 times. However, if you're working with sample statistics and you're looking at 20 or 2 millisecond time samples, then you're actually looking at that 40 millisecond wavelet 20 times, 5 times as densely as you would if you were just picking a peak or a trough or a zero crossing. This gives us a lot more information about the subsurface. One reason why multiple seismic attributes at one time are important is here's an example of 8 different attributes, and they're basically their wavelet, and all the red dots represent each sample. So you can see as you go from attribute to attribute, the information that you get from those wavelets at that sample are very, very different, and this helps us understand what's going on much better. And finally, when we're looking at the data, we're looking at it, I call these chiclets, but they're really voxels. But we're looking at basically information that comes back in the bin size of the 3D. So if it's 110 by 110, this distance is 110 feet by the sample interval. And most of the times, if I have 4 millisecond data, I can upsample 1 time to 2. Or if I have 2 millisecond data, I can go to 1 millisecond without introducing noise or artifacts. So I try to get the sample interval as small as I can to find out more about the vertical resolution in the rock. And whereas tuning thickness in the wavelet world may be 40, 50 feet at 10,000 feet, there is no real limit to what you can do in the neural classification world. The vertical resolution is, in the sample statistics, is based on the interval velocity of the rock from which the sample is taken. And so that that has no depth limitation, really. I've been able to find 7-foot thick sands at 11,000 feet. But people ask me all the time, how do I determine my recipe of attributes? And I tell them, well, a lot of it has to do with just general knowledge and the fact that I've been using machine learning for about 8 years, so I have a really good understanding in certain areas of the world what attributes are more important. But generally, I go through principal component analysis. This allows us to reduce a large set of variables, the seismic attributes, to a small set that still contains most of the variation in the large set. So here's an example of two attributes, attribute A and attribute B. And if you look at all the data points from those two attributes within your zone of interest, I don't do the whole darn seismic volume, I just try to keep the principal component analysis to that zone of interest that I'm working on. The first principal component is showing you the largest variation. So that's going to be the longest line right here. And the eigenvector is showing the direction of the line and how much variance or spread of data there is. The second principal component, which is the next largest variation, is orthogonal, or 9 degrees, to the first. Well, that's fine, and our brains can understand that if we're dealing with 1 or 2 or maybe even 3 attributes. But if we're working in the world where we have 12 or 13 or 14 attributes, we can't see in 14 different dimensions, but the computer can figure it out. And how that translates to reducing a lot of information down to something really usable is, here's an example of where I've gone in with 12 attributes. And I picked a line through a particularly good well because I'm interested in seeing what attributes are most important at my best production. And in this case, the first principal component is showing me 4 attributes. And these 4 attributes, in their relative percentages to all 12, account for more than 93% of the data of all 12. So the second principal component, now I have 3 attributes that end up being 81%, and they're 81% of the remaining information from the first 93%. So right here in 2 principal components, I've taken my 12 attributes and reduced it down to the 7 most important. So let's get on with the case histories. This first one is finding a sweet spot in an Oklahoman unconventional reservoir. This is some work I did about 1.5 years ago at the courtesy of TGS. TGS has great data in the Oklahoma area, and they wanted to know if machine learning could discriminate production in the Merrimack Formation, which is an unconventional reservoir in this area, and understand the accuracy in the neural classification results. Okay, so the assumptions and challenges were production is not necessarily related to geological changes. Porosity and permeability could not be calculated from the log curves they gave us because most of these are older wells. And there was they were anticipating difficulty in isolating specific production in all the wells through the perforated zone. So a decision was made to use only straight holes because of all the variables in completions with lateral wells, fracking, and how well they stayed in zone and so forth. And they gave me 35 wells. Now this is going to be kind of hard to see, but I've taken the cumulative production at the wells, and those wells in green have produced less than 35,000 barrels of oil. There's a little cluster over here of wells in pink and a couple wells over here, and those wells have produced above 50,000 barrels, 50 to 100,000 barrels. And of all 35 wells in this study, 1 well stood out beautifully, and it was called the Effie Cassidy #1, which was drilled in 1980 and has produced 240,000 barrels of oil and 2.23 BCF. The study area was approximately 195.5 square miles, certainly not all of the 3D that they have shot in this area, but a good portion of it. I'm going to focus on the south to north arbitrary, but in the study I looked at arbitraries both west to east and south to north, trying to hook up the better wells and the poor wells too. Now this is a time map on the Merrimack Formation, and the contour interval here is about 75 feet or about 10 milliseconds. This is a marly kind of limestone, and it's pretty fast velocity. Data quality is beautiful. TGS did a wonderful job doing this, and I have to say courtesy of TGS. But the Merrimack Formation that we're studying is between this pink line right here, that's the top of the formation, down to this yellow line, which includes the Woodford Shale. And the Woodford in this area is actually the source rock for the hydrocarbons in the Merrimack. And here's kind of a blow up of one well in particular, where you can see the top of the Merrimack down to the Woodford, which is just a trough in this area. What's important to also note is as you go from north to south, the section is gradually thickening because you're going into the Anadarko Basin. Now, that's significant because it also means that the source rock is also thickening. And that might explain why the wells on the north side of the survey were poorer producers than those wells on the south side. People would traditionally go in, drill the Merrimack, and absolutely just perforate the whole interval, with the exception, really interesting, of the efficacy well. Now, here's the results of the principal component analysis for the area. The green line represents kind of the median information for all of the first component analysis. But you can pick any one line in the 3D. In this case, I picked a line 754, which happens to be the line running through the efficacy, to see what attributes were important at that well. And in this case, the top 5 out of 17 wells, I believe, 16 attributes were sweetness, envelope, instantaneous frequency, thin bed, and smooth frequency. Okay, so with the exception of envelope, all these guys are kind of frequency-based attributes. Thin bed and instantaneous frequency especially are telling me that I'm looking for thinner beds in here, which we would suspect in an unconventional reservoir. When I look at the, and I did a lot of different SOM, and it's kind of an eyeball thing, but the one I settled on was a 10 by 10. It broke down the Merrimack in a lot of different patterns so that I could kind of see how it related to the logs. But what was interesting about the efficacy is that you can see that the perforation is here in blue, right here, and then all up this section. That they segregated out spots instead of doing just the whole darn area. And the lower perforations are interesting because they have this yellow and brown pattern in them. Okay, those are neuron number 71 and neuron number 72 out of 100 different patterns. And again, I'm working with a 1 millisecond sample rate here. My recipe that I ended up with was attenuation, envelope, Hilbert, instantaneous frequency, instantaneous phase, normalized amplitude, relative acoustic impedance, sweetness, and thin bed. But it's interesting that these lower perforations are specifically targeting this zone right here. Now, when we look at it close up, and we're looking at the resistivity curve, this is my density curve, this is my resistivity curve, and this is a rho B curve right here. The better resistivity for the whole interval is in these lower 2 sets of perforations, with the best resistivity being in this lower set, again, associated with neurons number 71 and 72. I think this is indicating a little bit sandier environment. The hydrocarbons you probably have a little bit higher porosity in here than the rest of the marl, and the resistivity is reflecting that. Here are the 2 neurons, 71 and 72, which I colored in the package to be pretty similar colors to the Kingdom display earlier. And what I've done is I've taken and I've kind of squeezed down the neural analysis to just include this lower zone so that I'm not picking up spurious information from scattered places around the rest of the wellbore and just focusing on this lower couple of sets of perps, primarily neuron number 71 and 72. And you can see that the Cassidy well right here has a combination of both 71 and 72. The 3 better wells up here that are in the median category did not have any 71, but they did have 72, the brown. And so what we can do, since we understand the bin spacing size and we know our sample thickness, we can go through a process and turn these chiclets or these voxels into volumes. And so they become like little platelets that you can see, and start associating volumetric information with the geobodies around the wells. In this case, I've created geobodies out of neurons number 71 and 72, and I've highlighted the geobodies that go through the efficacy well. Now, with a little bit of knowledge about the interval velocity and net to gross ratio and porosity and water saturation, you can actually get pore volume information that gives you information on reservoirs. I had a buddy working for a company whose group was involved in the Merrimack, and so he gave me some of the numbers to use for this analysis. And the end result of this dendritic-looking pattern right here, which I believe is key to the production of the well, is that when you get down to it, that well had a little bit over 118 million cubic feet of rock pore volume. And if you put the 14,000 feet per second, the net to gross of 60%, a porosity of 6%, because this is an unconventional reservoir, and a water saturation of 40%, you can come out with, and the recovery factor is 225 barrels of oil equivalent per acre foot. So that calculates 613,125 BOE for this geobody. And the actual for the well, when you convert the gas back to oil, is 611,685. So in this case, we are within a 1% margin of error on understanding where the production for the efficacy is coming from. And after I showed this to TGS, they said, okay, what about the other three wells, which were in the median category? Those three wells together had a combined total of 205.8 thousand barrels of oil and 1.38 BCF of gas. So here's an arbitrary line that goes from the efficacy up to those three wells, and here they are in conjunction. So you can see that there's actually 4 wells in here that were in the median category, but the magic circle number 2 Bernard didn't actually perforate neurons number 71 and 72, as we'll see in just a second. Those wells. Here's the production from the 3, and then here's the 4th well, but it didn't produce in the main Merrimack zone. It's producing from perforations that are above the top of the Merrimack in a lower zone associated with the Big Lime. And when you look at the neural information, you can see the brown number 72 again, okay, as well as the efficacy down here in 71 and 72 in the brown and yellow. Now there's scant occurrences of 71 and 72 between these 2 wells, and these scant occurrences have not been penetrated by any other wells. So we're going to look at this area right here, and when we blow it up, we can see that these 3 median wells are in the 72 neuron pattern. And while the 4th well did not produce from the 71 or 72 that they encountered, their production came from another group of 71 and 72 above the Merrimack, which is kind of interesting. So obviously those 2 neurons are showing production information. So I kind of looked at the dendritic pattern that made up the geobody for number 72 at this point, and I took the cumulative information from the 3 wells that produced out of the Merrimack section, and those 3 wells, the BOE was about 423,080 barrels of oil. Now, this whole geobody calculates to 481,681 BOE. So there's a big gap between what the geobody is saying and what the 3 wells were. However, there was a 4th well up here, the McKellar number Clydina, which actually did perforate in that neuron number 72 and produced 58,601 barrels of oil equivalent. So I added that well because it did perforate this geobody, added that well to the 3 down here, And the actual from the 3 was 481, and what I calculated from the geobody was 475. So here I am about 2% error from what was actually produced from the 4 wells in neuron number 71. So there's a very accurate way of looking at your production and understand what's going on. Then the last thing I did is I looked at the geometric attributes and to see what might be causing that zone, that 71, 72 zone. And this is a time slice from in approximately the level of the perforations in the Cassidy well. And you can distinctly see a series of channels coming down in the data, okay? So my suspect is, this is about 17 milliseconds above the top of the Woodford. My suspect is that there are probably little sandy channels that are coming through this area that have eroded down into the marlstone when it was exposed. And it's those sandy channels that give you your better production and resistivity when you can find wells that have hit them. Then I looked at the curvature volume, and I think there was a little glitch in their processing for some reason, to look at the fracture patterns in the area, because that also is going to give you some indication of why some production is better than others. And I ran a SOM with 2 curvature volumes and 2 similarity volumes, and here is just 4 neurons, 4 patterns, which give you the lineaments and the fracture system in this 3D at 17 milliseconds above the top of the Woodford, which is about the same zone as where the better perforations were in the good well. So the conclusions from that study is that SOM can be very effective in finding sweet spots in unconventional reservoirs, especially where there's changes in deposition, siltstones, calcareous sands, etc., and can be key to porosity and hydrocarbons. Geobodies can and are related to fine porosity streaks and can be back calculated to production for use in reserve estimates. It's also a good way of going forward to estimate new sweet spots which have not been drilled. But the key is understanding depositional environments, tying to wells with synthetics, and understanding the function of the attributes used in the analysis. Here's the conventional side of things. This is a study I just did earlier this year on a conventional play in East Texas. And my client has asked me to sanitize it as much as I can. So I can't tell you counties, I can't tell you wells or anything like that. But it's a significant field that I studied. And for the client, it had to do with a proof of concept. They didn't understand machine learning. They wanted to see how it would work on information that they had and what they'd been drilling. They wanted to see if on a sample scale could identify reservoir rock in Cretaceous sands below 13,500 feet, and to see if there were any remaining locations to be drilled in this field. Now, what they gave me was the 3D survey, which is the PSTM only. I had no AVO attributes, no offset stacks or gathers or anything like that. They gave me the wells, production, tops, and about 55 digital logs for the field. So here's a map on a key horizon just above the Cretaceous sand. And again, I've built a couple of key cross sections, a west to east cross section B and a south to north cross section A, going through the kind of heart of the field. The red boxes represent those wells on which I have created synthetics. And when you're working in the sample world, synthetics and a good tie to your data is critical, because if you're sloppy, then you'd be tying to a neuron that has nothing to do with your reservoir, and you'll make some mistakes. I had all the shallow wells turned off, so the only thing that you're seeing are those wells which are deeper than 12,000 feet. Here's the south to north arbitrary line in the seismic data. And here you can see the logs, and you can see the perforations in green, where the Cretaceous sand has been perforated. And you're coming up against an unconformable surface, so these come up and terminate at an angular unconformity, and then come up and terminate, and come up and terminate. So there's a series of different sands in here that are being cut off by this by this unconformable surface. And the key horizon has been mapped on the unconformity. Here is the west to east line. And since you're going quasi-strike to the deposition of these sands, it's not quite as clear and apparent that there's an angular unconformity here, but you can see some disturbance and see that there is kind of an unconformable surface. And what I've done also is I've put on the cumulative production for the wells. So we start at very poor on the west side. We get to some really good wells, and 25 BCF and 24 BCF. The best well in the field is this well right here with a cumulative production of 33.1 Bs and 1.77 million barrels of oil. And then you taper off again. This well across the fault is obviously down dip to the best, better wells, which seem to have some kind of structural advantage here. Again, I went through principal component analysis, and I used a zone from 30 milliseconds above the key horizon to 100 milliseconds below the key horizon. And again, the green line represents kind of the median information for the field itself. Each one of these blue lines they've done a principal component analysis along every inline. And this line right here represents the inline that went through the very best well, because I wanted to see which attributes were important at the good well. And in this case, in the first eigenvector, I have relative acoustic impedance, which is going to be important because that kind of tells you where you have porosity. I have envelope, Hilbert, envelope second derivative, and I have sweetness. And sweetness in here can be a hydrocarbon indicator, and it can be a sand finder. I ran Minisom, and I played with the recipe somewhat, and ended up with this recipe right here, where I'm using attenuation, and I'm using a relative acoustic impedance and sweetness as my hydrocarbon indicators. And then envelope, Hilbert, instantaneous frequency, instantaneous phase, and thin bed kind of are my stratigraphy attributes, if you would say that. And along the south to north line, starting at poor wells, and I again put the production on here so you can see what's going on. I have neural information at the better wells. So here, 47, 48, and 37 seem to be key. Numbers 37, which is a blue, and 73, which is yellow, seem to be key. In this well, which is 11.3 Bs, 47 and 48, and this well is 6 Bs, 37 and 38. So you can kind of see what's going on here in terms of the changes in the rock properties from poor to better in this area. Now on the west to east line, where I'm crossing through the better part of the field, I start in a poor sense, and I get better and better production. Here's 25 BCF right here, and I'm in 37, 47, and 48. Here's 24 BCF, and I'm in 37, 48, and 73, which is this little piece of yellow right there. And in my very best well, I'm in 55 and 73 with a little bit of 37 here in blue. Now, I talked to the operator of the field, and even though this well only produced 3.5 BCF, it's very significantly structurally hampered. And he said, but the rock in it was absolutely beautiful. It just happened to be structurally low and on water. But he said the permeability and porosities were every bit as good as what was in the best well in the field, which is probably why it's getting this yellow neuron. Then I went through the process of extracting the neural information right at the well, not just looking visually at the cross section, but this is a cross section showing the wells in the south to north, and then I'll have west to east. And I've used a designation to kind of break it down into their production. Poor being anything less than 5 BCF, fair being in the 5 to 10 BCF range, good being in the 10 to 20 BCF range, great being 20 to 25, and excellent, the one well I have that's excellent, is that well over 25 BCF of production. So I start out poor, poor, good, fair, great, good, fair. And again, I'm pointing out the neural numbers, the pattern numbers at the perforations. This red zone right here indicates the zone of perforations. And I put the perfs down here, and I put what the initial IP was, and then what the cumulative production was. so that you can kind of see what neurons are being repeated over and over again in these wells. And here's the west to east. Here's the well that's across the fault, but look at the 73 in it, and here's the 33 BCF well at 73. So it had excellent rock property and qualities. It just was structurally disadvantaged. But here's the west to east, and you got number 50 and number 30 in the poor wells 36 and 5, and then fair, you're starting to pick up some of the 48. And the 48 and 47s are kind of secondary neurons to the better ones of 55 and 73 and 37. So here's all of the neurons that were key to the production. There was a cluster of neurons in the poorer wells down here, and then the better wells, the good, great, and excellent wells were all in this range right here, 37, 47, 48, 55, and 73. And you can kind of see the distribution right here. Now I've got this sculpted down to 20 milliseconds from the key horizon, which is the unconformity, down 20 milliseconds, which catches 95% of all perforated intervals in the field. There were a couple of deep wells that went deep to catch a sand, but they were poor producers, so I didn't include that. But you can kind of see, and I put the key, the poor, the good, the great, the excellent, along the cross section here. So you can kind of see the distribution of those neurons. And then I'm breaking it down for the key top 3 neurons, which in my mind is 73, 55, and 37, and looking at what actually goes in to make up that neuron. So for 73, what's causing that to pick up some of the better production is you've got Hilbert, you've got relative acoustic impedance, again, which is my porosity indicator. You've got envelope, and you've got sweetness, which is my sand and hydrocarbon indicator. So that's really important. The number 55, you still have relative acoustic impedance and sweetness. They're not as high up in the list, and I think that's because you're probably dealing with a rock property that's not quite as porous or maybe quite as permeable as number 73. But you can see the distribution of that pattern in the wells in here. And again, this is my best well in the field. These are my cross sections right here. And then neuron number 37, while it still has relative acoustic impedance, I no longer have sweetness, that's rating very high, but I do have attenuation. So I would say that I'm still getting a porosity indicator, but I may be looking at more of a stratigraphic component now instead of just pure out and out hydrocarbon indicators. And here's the distribution for number 37 throughout this portion of the 3D. Now, one of the things I look at when I'm going through and evaluating an area is I like to look at the classification and the patterns, obviously. But there's another volume I can look at called probability or low probability. And when you're looking at the clusters that make up these patterns, here's kind of a spread of your data points, and the center of the cluster is right here. So you can see that there are a lot of data points around the center of the cluster, but there's still data points on the very fringe areas that are part of that cluster but are not at the center. And these are the most anomalous data points. They are the low probability data points. And why that's significant is that because they're anomalous to the cluster, if you're using hydrocarbon indicating attributes or you're using AVO attributes, these tend to be the places where you have your AVO anomalies or your hydrocarbons, okay? So I want to use this slide to preface what you're going to see next, which is I've taken the same patterns and I've turned everything off except the lowest 10% probability data points. And why is that significant? This field was discovered in the 90s. Well before they ever shot the 3D. And by the time they shot the 3D, and I think they probably over-drilled it because you can see the density of wells, by the time they shot the 3D, a large part of the field had been depleted. So I think in this case, the low probability volume is actually showing me my depletion. And I'm looking for zones that are left that are possibly not depleted. This well actually did not go deep enough to hit this zone right here, but I'm a little afraid of it, so I'm circling this zone, this area, and the well symbol is posting at the wrong end of the deviated well bore, so that well symbol should be posting over here, this area down here, and this area down here. So I have 4 areas that I have a lot of confidence in as zones or areas that may not be depleted from the rest of the wells. So I went through, just like in the unconventional case study, I went through and created geobodies. Now, the geobodies are all full data point geobodies. There's no geobodies created on just the lower 10%, or we can't parse a probability in the geobodies. So I'm having to take a percentage of a geobody that may cover a larger area to calculate my number of acre feet for these areas. And I'm just looking at 73, 55, and 37. I didn't include 47 and 48 in this case. So the first area to the south looks like this. There are no wells penetrating it, which is a good sign. It ended up with about 10,252 acre feet from these 2 geobodies. I've got neuron number 37, which is blue, and neuron number 73, which is yellow. Now I use, because we're deep and this is Cretaceous age rock, I'm using an interval velocity of 14,000 feet per second. I'm using a net to gross ratio of 80%. My high side case would be 25% porosity, water saturation of 30%. So I come out with 10,252 acre feet. Now, the field average for production is about 2,000 MCF or 2,000 MCF per acre foot and 54 barrels of oil per million cubic feet. And if you use those numbers and apply it towards the number of acre feet we have, this area has the potential of producing 20.5 BCF and over 1 million barrels of oil. That would put this estimate in the great category. If you remember the poor, fair, good, great, excellent. So that would be a great well to drill. The area to the north, the other area to the south, and keep in mind these are posting at the wrong end, is this area right here. Now, because this geobody is so big, I only chose to use about 15% of it to help me with my acre feet calculations. But going through and using the same numbers, I come up with something around 13.5 BCF and 727,000 barrels of oil. Still not shabby, but that would be a good category. Now, going up to the north, it's not quite as big or quite as good. So I'm down to one of the north areas. I only used a 10% portion of it because it's a much bigger geobody than what would be implied. But I've got a good stack of all the 3 key neurons right here, which is important. And so it would be somewhere in the order of 8.6 BCF and 466,000 barrels of oil. This would put it in the good category. And of course, changing any of these parameters, increasing or decreasing the velocity, the porosity, is going to change the calculation on the potential reserves. So you can play around with the numbers, and if you have an economic limit that you want, you could put it in the 15% porosity category and see if it meets your needs. But I'm using the porosities and the information from my very best well. So this is the most optimistic view. And finally, the last one to the north, because the geobody is so big up here, I did only use 10% of it. And it would be only in the fair category, producing 5.5 BCF and 298,000 barrels of oil. So again, you can play with the numbers, but this was based on information from the very best well in the field. So we have 4 areas that have potential of drilling, but there's still an economic risk here, or a risk for drilling. These are not cheap wells to drill. They're 3 strings of pipe. They run, drill and complete somewhere around $6 million. So you have to be very careful before you go poke a hole in the ground with these guys. So what is another way I can reduce the risk even further? we have we had an intern this year that put together a wonderful spreadsheet program for statistical analysis. And this is where we're really starting to get petrophysical information tied to the neural patterns that we're seeing at the wells. Here again, time-depth relationships are extremely important because you don't want to be sloppy with your synthetics. You want to make sure you have good ties. But in this case, we can put wells in. We can export the well logs from the software, and we can put well logs in, and we can give them petrophysical cutoffs for what is reservoir and what is not reservoir. And then we get an evaluation. We also have a theoretical chi-square table, which can give us a degree of relationship or non-relationship from the neurons to the wells, to the information, the logs. So there's a lot of things we can do with this. The chi-square can also, if you have multiple topologies, can look at a 5x5, 6x6, 7x7, and 8x8 and tell you which ones theoretically are the best number of classes to use for the well information too. In this case, I only used the 9x9, so I didn't go into that aspect of it. So I'm looking at 3 wells. I'm looking at 3 wells in here just to show you a sampling of what this program does. So here's a good well. It's well number 3 on the south to north cross section. And the production was 12.6 BCF and 176,000 barrels of oil. At the well itself, I have neurons number 38 and 41 that are part of the perforated zone here. So when I use a cutoff of a gamma ray of less than 60 units, anything greater than 8% porosity, and a resistivity of 8 ohms as the lower limits for what's reservoir and what's not reservoir, I do get in the analysis neurons number 38 and number 41 as being net reservoir. So the brownish area is no reservoir, the yellow in this case is reservoir. And even though I'm not using multiple topologies, the chi-square table is still telling me a null hypothesis is the lithological contrast sum neuron occurrences are independent of the presence of net reservoir. But the null hypothesis is rejected. So the alternative hypothesis is that there is a relationship between net reservoir and lithological contrast sum variables. So not only am I seeing net reservoir based on my cutoffs for the key neurons at the perforations, but I'm getting a chi-square confirmation that there is a relationship between net reservoir and lithological contrast variables. So that's well number 3. Let's go to well number 1 in the south to north, which is a poor well. It only produced 165 million cubic feet of gas and only 2,873 barrels of oil. But the key neurons at the perforations are number 74 and number 64. So when I put in the same variables, I'm using the same variables, less than 60 units in the gamma ray, 8% and 8 ohms. What I'm seeing here is I'm seeing very little reservoir and mainly non-reservoir at those 2 neurons. And so this is telling me that that's probably why the production was so poor. Poor rock quality at those perforations. Even though the null hypothesis is still rejected, saying that there is a relationship between net reservoir and lithological contrast sum variables. So I do know what little reservoir I have is right here at those 2 neurons. And then finally, looking at the very best well in the field, number 73 and number 55 are pertinent to the production here. And lo and behold, number 55 and number 73 are outstanding when it comes to net reservoir. Now, there is some non-reservoir in number 73, and I think that's because you have this little shale section right here on your resistivity curve, that you have this little shale section that it's going through. So it's picking up a little bit of non-reservoir information, but overall, most of it is reservoir. And again, the null hypothesis is rejected. So I am seeing a relationship between net reservoir and lithological contrast sum variables. So this is a really excellent way of taking the patterns that you're seeing and putting petrophysical limits on them to see if the patterns really have meaning for reservoir. So back to my 4 zones that are left behind from depletion. Now I probably have more confidence understanding what I'm seeing in the field itself to go and possibly spend the $6 million it's going to take to drill 1 or 2 of these locations. And that's exactly what my client was hoping to see. They didn't want to spend $6 million without having some kind of lower risk verification that they were going to have a high rate of success on this. And they're looking for partners in this area. So what does this tell you? In summary and conclusion, is that unsupervised neural analysis using multiple seismic attributes can show patterns in the earth that one can relate to reservoirs when calibrating wells. The use of geobodies can predict accurate volumes of potential hydrocarbons when one knows the correct input data. And the use of low probability data points can help identify stranded reserves in a field. And application of statistical petrophysical methods can verify and reduce risk in identifying reservoir grade rock in the potential stranded areas. This workflow is not one and done. It took me several different recipes and many different topologies before I came to the conclusion that the 9x9 I was using and the recipe I used was actually the best tie to the well information. And careful calibration to well information is what it's all about. Having good time depth relationships, good log curves that are consistent, and an understanding of seismic attributes is necessary for successful results. And finally, I would like to acknowledge TGS for allowing the presentation of the Merrimack study that we did. I want to thank my new East Texas client for the use of their data. And a big shout out and thank you to Carrie Lawton of Geophysical Insights for guiding me through the statistical analysis of the wells in East Texas. I could not have put that part together without her. And so if there are any questions at this point, I'll be glad to answer them.
Okay, thank you very much, Deb. That was a fantastic presentation. So I just wanted to have a reminder for everyone. It is now open for questions. And you can access the chat room from the big blue button right below the presentation that says Ask Questions. And so there was one question, Deb, that came in right like during your presentation, and it was how is the how different is the sweetness attribute when it behaves between like oil and gas? So what are the different kind of responses?
Can you hear me okay?
Yes.
Okay. I have been using sweetness as a hydrocarbon indicator in the Gulf Coast, primarily clastic environments, for probably about 15 years. And it's something that needs to be calibrated to the wells in the 3D. It's an excellent sand finder, but many times it's also a hydrocarbon indicator. If you're looking, say, at the Yewa in the middle of a big shale package, anywhere you have a sweetness anomaly, you can pretty much be sure that you're going to have sand. But you need to look at other productive wells to determine if that sweetness anomaly is really a hydrocarbon indicator or just a sand indicator.
Sure. So there was another question that came in that was just asking whether or not you've ever tried random forest classification and whether or not Paradise does that. But there has been a response that that is currently in R&D. But have you ever tried that anywhere else?
No, I'm perfectly happy with solid classification, and I've used it probably in 300 different surveys at this point in the last 8 years, and have had excellent results. So I haven't tried any other type of any other type of supervised learning process.
Fantastic. As of right now, there are no other questions. Does anyone else have any questions? Maybe we can give them a minute or two. Can supervised learning be used to directly predict porosity and net to gross, etc.?
Well, I'm not using supervised learning in this case. I have found that when it comes to the subsurface, that the unsupervised machine learning is actually superior. We don't know going into anyone 3D what the natural patterns in the data really are. And if you're trying to restrict it or you're trying to control it, then you're forcing patterns that may or may not be there. So the unsupervised learning methodology to me is the best for discovering what's in the subsurface.
Great. Has there been any case of predictions of phase of hydrocarbons? Have you
Predictions of what?
have there been any cases of predictions of phase of hydrocarbon?
You're saying phase of hydrocarbons?
Phase, yeah, the phases of the hydrocarbon.
No, it's. I have a lot of people that ask me how easy it is to find oil versus gas, and it's not easy at all because oil is so close to water in the subsurface. Um, but believe it or not, subtle pattern changes can occur using the unsupervised methodology and can differentiate between oil, gas, and water. I've used that in reef systems a couple of times with good success.
Fantastic. Thank you. Um, if there aren't any more questions, I think that is the last one. Um, I want to thank you for the wonderful presentation. It was very informative, and I want to thank everyone for attending our last breakout session. There will be a final presentation back in the auditorium at 3 o'clock, and the subject is the impact of machine learning on the oil and gas service industry. So thank you very much for participating. Have a wonderful day, and thank you, Deb.
Thanks.